And hello all. Folks are slowly trickling in, so we'll just give another moment or two to allow some more people to get signed on, and then we'll get started. And just for the sake of time, I think we'll go ahead and keep rolling, and folks will just get allowed in as they sign on. So yay, thank you all for joining us for our September 2025 webinar. We are excited to have this month's presenter from the Precast Concrete Institute, or PCI. And for a little taste of what we'll be discussing today, the precast, prestressed concrete industry is embracing environmental transparency through standardized life cycle assessments, LCAs, and environmental product declarations, or EPDs. Producers around the country are committed to engaging with the AEC community in the common goal of creating a resilient, healthy, and sustainable built environment. This presentation will explore how the industry is measuring embodied carbon through regionalized EPDs, implementing process improvements to reduce global warming potential, GWP, and leveraging precast concrete's inherent sustainable attributes, including durability, energy efficiency, and resilience. Attendees today will learn how EPDs are transforming sustainability conversations and enabling data-driven decisions for low-carbon concrete construction. We'll get into this more shortly, but first, we'll start today's presentation off with the agenda and some announcements. So first, for the agenda, I'll start for the first 5 minutes or so with welcome, news, Carbon Leadership Forum overview, and our speaker introduction. Then I'll hand it over to our speaker for about 45 minutes to speak on their topic. And finally, we will reserve the last 10 minutes or so for Q&A. Now for a brief Carbon Leadership Forum overview. So thank you for joining us. We are the Carbon Leadership Forum CLF Rocky Mountain Hub. We are made up of 5 co-chairs currently, which includes Michaela, Victoria, Annie, Dorian, and myself. If you want to get involved, be connected to our newsletter, feel free to reach out to any of the folks listed here. And in our webinars, we also like to amplify events, new documents, and announcements related to embodied carbon. And today we bring you a few noteworthy updates. First, there's a new resource for structural engineers hot off the press. The Structural Engineering Institute and ASCE has published the first edition of the pre-standard for assessing the embodied carbon of structural systems for buildings. The pre-standard was developed to align embodied carbon methodologies across the profession and to support the SE 2050 commitment program, helping engineers take meaningful steps toward a lower carbon future. And then next up, as of last month, the Carbon Leadership Forum HQ, Rocky Mountain Institute RMI, University of Washington, and one of our former CLF Rocky Mountain co-chairs, Matt Humklaus, released a report which provides an assessment of embodied carbon from U.S. construction materials and explores pathways to align with a 1.5 degrees C global warming limit. Both these reports are worth checking out. If you'd like links to any of those, feel free to follow up, or I know they are linked on LinkedIn and the CLF website. And finally, as a reminder to everyone, there is a sales and use tax exemption available to all Coloradoans that purchase approved eligible decarbonizing building materials. This exemption saves you 2.9% on material purchases. And if you're interested in learning more about this, feel free to follow up with me after the call or visit the Office of the State Architect website. And then if anyone is new today and interested in what the Carbon Leadership Forum is, we have some clarification here on both the national organizations as well as the regional hubs. And with that, the National CLF or CLF HQ is an independent nonprofit which hosts research, education, and cross-sector collaboration that drives the data, tools, and policy changes needed to eliminate embodied carbon from buildings and infrastructure. And then the hubs are regional groups of individuals committed to embodied carbon reductions, all hosted by the National CLF. In addition to our regional hubs, CLF also has focus groups that you can join if there's a topic that suits your interest. There are 15 total focus groups as shown here. And the bottom 5 are the newest additions. So the CLF truly has a number of ways to get involved if you want to act with others to reduce embodied carbon. If you're interested in joining the Carbon Leadership Forum, then create a CLF account and get started. Other than that, here are some of our CLF Rocky Mountain resources. Use the links here, or they're all available in our newsletters, to follow us on LinkedIn, view our YouTube channel, and more. And now with the CLF intro being complete, I'd like to now introduce today's speaker. With us today is Jim Schneider. Jim is the Executive Director of the PCI Mountain States chapter, which covers Colorado, Idaho, Montana, Utah, and Wyoming. Schneider has been working with architects, engineers, and building professionals for nearly 2 decades. He also has been a writer and editor of several business publications, including EcoStructure, Architect, Plumbing Engineer, and Metal Mag. He currently is a regular contributor to several national and regional industry publications, including Retrofit, Retrofit Home, Green Building and Design, Accent in Colorado Design and Construction. Schneider is a lead AP and is passionate about efficient and sustainable design. And with that, I will now pass the presentation over to Jim to speak.
Thank you very much, Bailey. I appreciate the kind introduction, and thanks to you and Michaela and Annie and everybody at CLF for having me here today. I'm excited to join the group. All right, I'm going to go ahead and share my screen. Hold on a second here. See if I can get this right now. Hold on, I got to go into presenter mode. Bear with me for a second. So yes, just briefly, I am the Executive Director of PCI Mountain States, and as Bailey mentioned earlier, PCI is the Precast Prestressed Concrete Institute, and that is a national organization based in Chicago. Okay, do I have the screen up right now?
Looks great, thank you.
Excellent, thank you. All right, and I represent the mountain region, which is Colorado, Utah, Wyoming, Montana, Idaho. We have PCI certified precasters all around the country. And I represent the producers here in the mountain states listed here. Some right here in Colorado include Encon, StressCon, Plum Creek Structures, and Wells. And I will note also for those of you who are collecting AIA credits, this is registered for AIA credit, HSW. I should be able to get an attendee list and any numbers like that after the presentation. Or if you want to send me your information, my email will be at the end. And I will also note that we were able to get GBCI self-reporting credit for this. So if you are interested in that, I would also say reach out to me. My email will be available at the end, and I can get you squared away with that. So going over the learning objectives today, we are going to be analyzing the role of environmental product declarations, EPDs, and LCAs, and quantifying the environmental impact of precast concrete, including in understanding the difference between cradle-to-gate and cradle-to-grave methodologies. Evaluate how regionalized industry average EPDs for 2025 provide transparency and global warming potential and other environmental impact categories, enabling architects to make informed material selection decisions. We'll identify some attributes of precast like offsite construction, durability, energy efficiency, and some of those things that just by its nature are helpful to the sustainable design of a project, and then apply knowledge of precast durability advantages and lower carbon potential to design decisions that align with hazard mitigation, community safety, climate adaptation goals, while reducing long-term maintenance requirements. I've already gotten a little introduction there, so thank you for that, Bailey. I will add as a note, like I'm coming into this from my background. It originally was in publications, and I was a magazine editor for a long time in a lot of different types of publications, and got to work with PCI and in green building publications, and did really become interested as, kind of a geek out thing myself, though I'm not an engineer, in the potential of concrete and what we can do with it, both from a structural and environmental standpoint. And just to share a little bit about how I do, geek out about concrete, I'm also the dad of two kids, and I talk to them about it all the time. And one time I was actually on a podcast called This is Concrete, talking about sustainable innovations in concrete, which we'll touch on here. And I was driving with my kids, and had the podcast had just dropped, so I was listening to it in the car. And after a couple of minutes, my daughter said, "Hey, Dad, is that you on the radio?" And I said, "Well, yes, it is. I'm on this podcast called This is Concrete." Oh, and I drove a little further. I looked back in about 5 minutes, and this is what I saw in the back of the car. So maybe they aren't quite as interested in the topic as I am. However, I can tell you, I think it's pretty fascinating. So you're going to bear with me as I geek out on it here. But part of the reason we're talking about this is the fact that, as you all know, the world is changing. We have lots of reason as a built environment to really be paying a lot of attention to our impacts, our long-term performance, and how we interact with the environment around us. The built environment has a significant impact on carbon, on energy, on materials. And so we really have to think about how we better use all those things in a way that is useful to the built environment of the future, but also works in harmony with communities and the environment. Buildings account for about 28% of global emissions each year. The building industry consumes about 40% of the raw materials flow of the entire global economy. EPA has estimated that 569 million tons of construction and demolition waste were generated in the US in 2017. That's more than twice the amount of generated municipal solid waste in that time. So for those reasons and many others, I kind of think we have to think about buildings and materials a little bit differently. It's both in the initial impact of it and also the durability, the adaptability of the long-term performance. Statistics, just a few of them listed here that I'm sure are no secret to anybody out there. We are seeing an increase in severe storms and in fire damage to buildings. So buildings are facing more stress. And while they're doing that, we're also seeing, the fact that buildings are creating this environmental impact through their energy use and through their materials is creating some of the environment for climate change, which is creating the environment for more severe weather and fires. IPCC reports in the recent years show that as well. So it's essentially, I think that we have to really think about how we build for tomorrow, which is both taking into account how we mitigate the impact of climate change and also how we respond to what is already happening. We have to be thinking about climate adaptation and other pieces of the equation, as well as trying to mitigate our impact. So some of the ways that precast, pre-stressed concrete can help in a sustainable design, and I'm somebody who believes that it's really the design and how you utilize materials is a big part of the equation on what makes a building quote unquote sustainable or resilient. And so there are benefits and attributes of precast and of concrete broadly that can really help in a sustainable design. And some of them with precast, pre-stressed concrete are the fact that it is an offsite construction method. So there's a lot of efficiency there, very durable and long lasting life cycle performance. So you get some of that long lasting, resilient, adaptive type of performance. Good energy performance, good indoor environmental quality, material efficiency, and design flexibility. So those are kind of, what I'm kind of starting off with here is a few of the things that we've talked about as an industry for a while that are, well-known benefits of using this type of material. And one of those can be energy efficiency, particularly when we're talking about with precast pre-stressed concrete. A common component we use is a insulated sandwich wall panel, which is where you have a interior and an exterior width of precast pre-stressed concrete with a layer of continuous insulation sandwiched in between. So really, when we're talking about how we create energy efficiency in a building, it's by managing that thermal energy flow, that heat flow. We do that by using insulation, and then also by eliminating thermal bridges and making sure there's no metal that's going through the envelope system that creates cold spots that can lower the overall performance of the wall. Make sure you eliminate air and moisture leaks. And as a bonus, with concrete, you can utilize the thermal mass. So basically, when we're talking about thermal bridging, it's making sure you have a wall system that doesn't create these breaks in it where you have metal either connectors or metal studs or anything like that. It can really impact the performance of a wall, as shown by these thermal imaging of a stud and cavity wall that might be a material R value of R19, but actually performs at closer to R9 once you factor in that thermal bridging. Now, with a precast sandwich panel, we use non-conductive ties that hold the whole thing together so we don't get that thermal bridging. You have insulation built right into the system. And then thermal mass, I'm just kind of briefly touched on some of the stuff. And if anybody wants to go deeper into it, I'm happy to connect afterwards. But essentially, thermal mass is the quality of concrete where it acts sort of like a thermal battery. It slowly absorbs and slowly releases heat. So what it can do to the performance of a wall system is shove the peak heat load to off peak hours for electricity, so it's cheaper. And more importantly, it actually makes the peak smaller. This comparative chart actually shows a few different wall systems, that smaller peak being a precast insulated panel. And so what happens is it creates more even temperature. The HVAC doesn't have to work quite as hard. So there are some physics benefits that you can actually calculate and factor in with precast. And this is an example of a precast sandwich wall panel, what its material R value might look like. Because the material itself, whether we're talking about concrete, steel, wood, anything, doesn't really give you much insulating value. It's obviously the insulation part that does. When you add all these together just as individual parts, you get that material R value of 11.65 for this sandwich wall panel. And this is actually from a case study of a project in Fresno that utilized the sandwich wall panel much like that, and then ran the thermal mass calculation and showed that that wall actually performed at R 26.1 rather than the 11.33 of its material R value. So it almost doubled the effective R value of that wall. And in that case, they were able to downsize their HVAC by 37%. So those are some of the examples of how precast can be used in an energy efficient manner. It's also very materially efficient. As concrete goes, it is plant produced. So under very controlled conditions, where that comes to mix and just the amount of materials used, there's very little waste. So it creates cleaner, neater construction sites, a lot less room is needed for staging on the site. It's a very efficient off-site construction method. Use steel forms to cast structural products, so those are used over and over again. You get a lot of uses out of those. Specialty shaped molds are stored for future use, depending on, it's usually amortized by how many pores we're going to have in a particular form, the type of material that's used to make sure we get the most efficiency out of it for both economy and environment. It can be recycled and reused, crushed down and used for things like road base. And we're even seeing some work being done that I'll touch on later about trying to use crushed concrete as partial aggregate replacement in new concrete. But we can also be engineering for adaptive reuse of components as well. And one really cool example of that was the Olympic Stadium that was built in Atlanta back in the 90s for the Olympics back then. It later became Turner Field. But they actually designed it with a number of riser sections that were designed to be removed after the Olympics and transported to local high schools for their athletic facilities. So there's potential of doing things like that, or kind of future-proofing different designs for precast to reuse them as parking structures that can be designed with certain floors to be retrofitted into office later, those kinds of things. So it offers some flexibility in that respect. And then resilience is an important part of the equation. I think the more we talk about truly sustainable design, we're also talking about resilience. We're talking about climate adaptation. We're talking about a building that can stand the test of time and hold up against the conditions that already exist and that will inevitably become more severe over time. So a resilient building delivers long and effective service life, provides safety and well-being to occupants, which is really the first responsibility of any building, can effectively resist hurricane and tornado force winds, earthquakes, fire blast incidents, minimize disruption and recovery time, provide sufficient functional resilience to ensure continued performance even in the face of an environmental challenge or disaster, provide benefits for insurance over the long term. And we're starting to see a shift in that industry and more demand for resilient construction, and meet the demands of communities that are seeking structures and building that perform beyond code, like something that isn't just the bare minimum, but something that you can really rely on and use into the future. So precast, pre-stressed concrete is a very strong, durable material beyond some of its initial upfront benefits. It just does last for a very long time. It stands up really well against fire, against storms, all kinds of things that can happen to a building. In terms of storm resistance, we see it very often used for FEMA storm shelters, which sometimes have been built into school gymnasiums or things like that that can be part of a community design So it is a very strong, durable material, provides excellent protection against high winds, storm surge, in hurricane zones, different types of weather conditions that can affect it, which is why it is used in those types of designs. And the kind of illustrative video that we have from the industry research that was done years ago in this area was that we did a wind cannon test to see what a couple of different wall systems would look like in the event of like an EF5 tornado where you have 100-mile or whatever it is mile-an-hour winds. So this was actually a wind cannon test shooting a 2x4 at 100 miles per hour through or at a couple different wall systems. That was a vinyl wood frame, and you can see it punctures that pretty easily. Brick and wood frame. It also, creates a little bit of resistance there, but still gets through and damages that building. And next is a brick and steel frame. Effectively sharpens the projectile and makes it more dangerous. So that's no good, but still doesn't stop it from penetrating the building. And then we have a precast insulated sandwich wall panel, and you can see how it basically just bounces off. Like if there's any damage to that wall, it's aesthetic and it's a touch up. So first of all, the people inside were kept safe. And secondly, the building's able to continue functioning, which to me is kind of the definition of resilience. Durability is the capability of a building, a material, a community, a person to take an impact, to take a punch. Resilience is taking it that next step and saying, can you continue to function? Can you still continue to do your job and move forward after that? And one example of where this was, kind of the resilience and adaptability of the material, if anyone remembers the tragic tornado that struck Joplin, Missouri back in 2011, that was national news at the time. And it pretty much destroyed that town. It was a significant loss of life and property. But one of the buildings that did survive that storm was this 96,000 square foot Shopco. It was a precast big box space that really hadn't been used for a number of years. They were able to retrofit that into the new Joplin High School in just 55 business days. So, to me, that's a story of adaptability. The material is able to change its use of that building pretty quickly and easily. And those students were able to return back to school on time. So that sort of is the true definition of resilience, where that piece of the community's activity was able to continue as normal in the fall in just a really quick amount of time. At least they had that piece of normalcy to cling on to. And the entire town was rebuilt in resilient and sustainable fashion after that. Just another kind of interesting example of designing for climate adaptation and thinking ahead for the future is a Statue of Liberty Museum that was designed in the aftermath of Hurricane Sandy. So, a number of things they did here was set it above the 500-year flood levels. Hollow space at the lowest level of the museum has 84 rectangular cutouts that allows flood water to flow into the base, and that reduces the risk of pressure on the structure. Sustainability was a primary goal here, and they used insulated sandwich panels and thermal mass to achieve some of the energy performance they wanted. Also, a green roof, which precast was a part of that design as well. So there were a lot of ways that precast was able to help make that design possible, and it's just clearly a building that it was LEED certified, and I'm forgetting which level, but it was designed both for sustainability and for thinking to the future and the kinds of weather that an East Coast facility like that is going to have to deal with over the years. And of course, we talk a lot about and have for many years about the long-term performance benefits of precast concrete. There is, of course, an embodied carbon element to it that is part of the equation. And really, materials in general do have impacts in this area. So we have to kind of think about the initial impact and the long-term impact. With concrete, the material as a whole contributes 6 to 11% of global CO2 emissions. Most of that comes from Portland cement. We're going to talk more about that a little bit later in the presentation. Steel, also very impactful in this area, about 10% of global CO2 emissions. Wood, it's a little bit more wibbly wobbly. There's less initial or like easily trackable emissions, but there are things that come from biogenic carbon loss, transportation, and other things like that that are kind of beginning to be identified. And this is just from a study from the International Institute for Sustainable Development that went into some of the difference between upfront and long-term impacts in terms of carbon from different types of materials. And what you can see in this was obviously that light blue manufacturing impact is higher with carbon or with a higher carbon impact of concrete over wood. Construction a little bit higher as well. they start to factor in biogenic carbon loss with some of the wood products there, and that evens it a bit. And then you start to factor in the use phase, which is about where approximately 95% of the impact of a building in terms of carbon and energy comes from its operation and its use over time. So when you start to factor that in, there are benefits of a material like concrete that can basically, over the long term, balance the ledger a little bit. So there's essentially what it gets down to me is that all building materials have an impact. It all has a cost. And how do we leverage that and utilize it to the best way possible to get the long-term performance that we're seeking, as well as mitigate its impact up front. Precast and concrete as a whole does have an upfront carbon impact, and that is, somewhat it's mitigated over the life cycle by its performance. However, that being said, we also recognize the importance of doing something about the initial embodied carbon and trying to change the metric there and bring down that impact so that it can perform even better and be an even more impactful building solution for us into the future. So next, I'm going to talk a little bit about where we are as an industry where it comes to some of these reporting and transparency and getting into the TLAs, as I like to call them, the three-letter acronyms, PCRs, LCAs, EPDs, and everything else. So where we are, there is, of course, overwhelming scientific evidence the Earth's climate is changing. We know that. We all know climate change is affecting the planet and have a role to play in reducing the emissions. So why do we focus on concrete? I talked earlier about the fact that the built environment, construction in general, has such an enormous impact by percentage around the world. And you can see this in, this pie chart kind of shows which different impacts happen around from a carbon standpoint. Transportation, everyone always thinks about cars, but it's 23% versus building operations, which are 28%, materials and construction 11%. So it's a big deal. Like, we have a big footprint, and any impact we can make in improving our impact really does change the dynamic around the world. So cement is the main driver of the impact of concrete. If we could have a magic wand and somehow make concrete well without cement at all, that would be great. And maybe that someday we'll get there. In the meantime, we are trying to find ways to use it in a more efficient way, to find ways to replace it that still give us the performance that we need and deliver the aesthetic, the versatility, the performance, and all those things that we want to see in concrete too. So in the current state, we are seeing an evolving awareness and focus on how we even think about buildings and how we think about quote unquote sustainability, which is a term that's kind of going out of fashion. And that's maybe not a bad thing, because we really can think about what is the most effective way for us to build. Like, really, this shouldn't be about, I don't think we're ever really going to move the needle super far by trying to make it an altruistic thing. What it really is about doing buildings better, doing business better. How do we do it more efficiently, less impactful, and coming at it from that direction? So we want to understand the environmental impacts of our material and our industry, especially where cement is concerned, and figure out how we work that. And the perception of concrete is a notable thing. I mean, I run into this all the time. There's plenty of folks who just think concrete on its face is bad, and there's plenty of reason to think that, but there's also plenty of reason to think that it has a really important role to play. So lack of clarity also on the differences between different types of concrete, because there are different types of concrete, and how we use them and how we create them. Focus on initial versus long-term impacts. Both are important, but we really do have to factor the whole thing into the equation. And then prescriptive versus performance-based specs. We as an industry really think there is the benefit of performance-based specs, which is, getting to that point of saying, here's how we want it to perform, and then we'll let the producer or designer get to that point the way they need to get to it, rather than setting the actual material targets that may not be relevant or may actually be a hindrance to getting to the kind of performance you want. There are lots of industry efforts to decarbonize cement. Portland Cement Association has released a roadmap to carbon neutrality. Global Cement and Concrete Association, CLF, right there. And our own industry, PCI, has been putting a lot of effort into this for a long time. I worked at PCI National back in 2004, and I want to say it was maybe 2006 that we formed our first sustainability committee there. that has really taken on a new life in the last several years and has become very active at a board level, even in our organization, where it's kind of become a priority all across the board, which has been part of our big push to gather industry data and EPDs and have this transparency. So we as an industry have invested a lot of time and energy into producing EPDs, tracking carbon and talking about sustainability among ourselves and to the outside world because the market demands it. Policy environment is requiring it. Architects and engineers are looking to design lower carbon buildings. Owners and developers are setting climate targets and embedding sustainability into their government practices. And governments at various levels are enacting buy clean policies. We certainly have that right here in Colorado that require EPDs. It's something that here in Colorado, we can take pride in the fact that we're the first Department of Transportation in the country to have required EPDs, and we're a leader in many ways here. So it's been a good inspiration for our industry to respond to that and really push forward on getting a good state of where we are. And then, from there, we can build on where we're going to go. So concrete is the most consumed material on earth after water. There's a heck of a lot of it used. And really, when we think about the scale of construction, looking into the future, I think the estimate is that the equivalent of a new New York City is going to be built every 3 months or something like that. We just simply can't build at that scale without concrete. It's locally available materials. In a lot of places in the world, it's the most effective from an economic standpoint. So all of that said, we have to figure out how to do it better. But concrete amount accounts for about twice as much material by weight as all other construction materials combined. Yet it accounts for about only 8% of global CO2 emissions. So part of that big number in emissions is from the fact that we just use so much of it. So once again, being able to change the mix on that and hit to a better place, any improvements we can make in concrete can make a really big difference worldwide. So talking about an EPD, I'm sure most folks here are probably familiar, but just in case you're not, the process essentially goes with the beginning of a product category rule or PCR, which sets the rules, calculation requirements, and guidelines that get you to a life cycle assessment, or LCA, which is the method to assess the environmental impacts across a product's life cycle. That gives you just a ton of data that is really kind of difficult to make sense of. And so what happens then is that is boiled into an environmental product declaration, or EPD, a third-party verified, internationally recognized label that has a public disclosure of life cycle environmental performance that's based on that LCA. So let's take a look a little more closely at what's measured in an EPD. Most published EPDs follow what's known as an A1 through A3 scope. You'll often hear this referred to as cradle to gate. That means capturing all the environmental impacts that occur from the time the raw materials are extracted. For us, that would include primarily cement, aggregates, and steel, all the way through to the end when you finish the precast element and it's loaded for shipment at your plant, which is the gate. So that scope includes A1, which is raw material extraction and upstream production, A2, transportation of those materials to your facility, and A3, all on-site manufacturing, assembling processes, including batching, casting, curing, any reinforcing work. This does not measure downstream activities like shipping to the site, installation, or end-of-life performance. So what you're looking at in this chart, what's squared off here is what we're talking about with cradle to gate. Everything else, which is a significant part of what that building is doing over time, isn't really included in this, which is something where we hope to see more of a shift into the future into more whole building modeling. But for now, we are kind of focused on trying to understand the cradle to gate A1 to A3 impacts. And that is the A1 to A3 scope is where the majority of embodied carbon in most products come from. For us, again, that's as precasters, that's mostly the steel and cement that goes into the material. So how do we get to this raw material? This is where the LCA comes in. Each EPD is built from a complex calculation that models the environmental impacts of producing 1 unit of a precast product from cradle to gate. How producers input real operational data we have a tool that we're using as an industry through WAP that a lot of our members are using. A few others have done others. But it'll input data like how much cement, fly ash, slag, rebar, aggregates are used, what kind of energy sources run their plant, how far do materials have to go to get there. That all gets processed through the software and matched with a life cycle inventory database like EcoInvent, which contain upstream environmental impact factors for each material in the process. So life cycle input, the result is standardized environmental indicators. You get um, global warming potential, GWP is what we're mostly talking about. Also, you can get into things like ozone depletion potential, acidification, different types of things that are studied in EPDs. So from national to regional, here's why that matters. We've recently released regional EPDs. Now, historically, PCI in the past had published one national industry average EPD for each major product category, which was a good start and it provided some transparency, but it was something we needed to build on because, frankly, the United States is a big place. Regional differences in energy sources, cement blends, transportation differences, and even production practices can vary dramatically. A plant in California using type 1L cement and renewable electricity is going to have a very different carbon profile than one in the Midwest using traditional grid power and traditional cement. So the national EPD, those being averaged together, really wasn't giving any real good picture to anybody. So by regionalizing it, we can create more accurate and meaningful benchmarks for where a place in the country actually is. And that's a good, for us to build on, you have to first know where you are. So PCI producers, over the course of 2024, production data from member plants is gathered across all regions. In total, we had 64 producer plants participating in creating the 2025 regionalized EPDs and industry-wide EPDs. And so now we just rolled these out in the last few months, and they're broken into these regions. So of course, we're in the PCI Mountain States region there that allow that breakdown to happen. So we have those regionalized EPDs within our area there, and then also many plants, including the ones here in Colorado, have their own EPDs. So just kind of gives you a snapshot of what happens when producers are gathering this data. They have this software, they enter in all these different types of products and impact categories and things like this. And it gets, I'm just going to kind of go through these quickly. And that's how the EPD is assembled. So they're able to do this. It's a lot of input work and a lot of kind of understanding, what transportation means, like what's point A to point B and how does that factor in. So a lot of that has gone into educating our industry and also getting our producers gathering this information to give us the good baselines that we have. So now we have this regional EPD that is third-party verified, declared units, third-party verification, LCA reference to WAP. This confirms the life cycle stages declared in the EPD. So again, it's that cradle to gate that we talked about. Following introductory section, the EPD then turns to reporting the emission impacts of the product. The first column on the left identifies the environmental impact being measured in that case. After reviewing the environmental impact data for structural concrete in each of the region, the EPD shares a table that summarizes the minimum and maximum values experienced in each of the regions, giving an idea of the variance within that region. That min-max report focuses on top-line environmental impacts. So now we've seen how the producer data flows in. What does this all tell us? This is where the real value comes in, is being able to make sense of what any of this data means. So, for example, we can see which materials and processes are contributing the most to global warming potential, and then compare those patterns across regions and start to build strategies that can improve our performance over time. So this is why getting this information and baseline matters. This chart is based on data contributed in our own structural precast EPD that breaks down global warming potential by material and process impact input categories based on weighted industry average. No giant surprise here. Cementitious materials, especially Portland cement, are the dominant contributor. Other contributors include steel reinforcement, aggregates, plant energy. So we have some of that data that shows us that. This is from PCI Mountain States region specifically. The A1 total, 70% of precast GWP is embodied in the raw materials we use to produce the products. Cement and steel alone account for 63% of the total GWP. Under A1, you'll see there's also manufactured aggregates. It's very little in some regions, more pronounced in others because it is energy intensive. It is specifically called out in the reporting. It is interesting to note that natural aggregates as material don't contribute much to the total. Rock and sand is not an energy intensive material, it's simply extracted from the earth, grade 8, and ship. And it is in the shipping where aggregates that use, so kind of how far it goes is where that impact is going to come from. A2 total in PCI Mountain States is 13%. A3 is the energy used in plants, and that comes up to about 19% in the region. And that's just an example from another region, PCI Midwest, and their structural. So here, 74% of GWP is in the raw materials. Cement and steel alone account for 72% of that. How do we use these? Of course, LEED version 4.1 and also LEED version 5 are request EPDs, so these are helpful in that. Also, just for initial benchmarking, communicating with design and project teams, kind of where we're at generally across the board, and not just our industry, but all, I think, is getting an idea of what our baselines are right now, what's realistic, and then how can we improve from here. And it's also important to think about sort of the cradle to gate and cradle to grave, how you're talking about something. Because if you're comparing two things and one metric is cradle to grave and one is cradle to gate, they're obviously going to be very different. So make sure you understand what it is you're talking about. And part of the reason that we're doing this as an industry too is because too often we were being lumped in with ready mix, which is a very different animal. So just as an example, this is a slide that Emily Lorenz in our industry prepared for a presentation she did, and it represents A1 to A3 snapshot of precast, showing all the things we've all discussed, like all the things that are going into that snapshot. Now, if you look at ready mix as a comparison, like all these things come out of that ready mix. So that's not part of their overall equation. That has to come in different places. So because precast is including the strand that's used in it, the reinforcement, the curing, like it's a different process and different materials used. So we wanted our own data so that we could be baselined and compared to our own type of material and our own process, rather than being kind of Frankensteined into a different process with ready mix or a different type of concrete. I think again I talked about the difference in scope from cradle to gate. It's just that actual production right up to the point the product goes out there. When you're talking cradle to grave, then we're getting into shipping to the job site and construction and performance over time, operation, maintenance, all that stuff, and end of use, end of life as well. So what's going on ahead is actually there was a meeting just today, I believe, for our new PCR, which is under development, the new product category rule update. That's going to be taking effect next year at some point. So our industry is getting together on revising that for the future. And so that's kind of where we are as an industry right now, as a right now snapshot. We do have good regional data. We have some good plant specific data, and we're finally creating a good framework to be able to gather that and be able to create that kind of transparency that the industry demands at this point. What I also want to talk a little bit about quickly is that we are making an effort as an industry as a whole, whether that's precast concrete, the cement industry, ready mix, all of the concrete industry as a whole, to figure out ways to reduce the cement use and impact of concrete across the board. So some of the innovations that are in the works, some of which are in pretty common use already, others of which are just kind of being scaled up and studied, are really about maximizing the long-term benefit of the material by addressing the fact that cement is the real upfront carbon issue. So how do we better use it? How do we use less of it? One goal of us is just to try to use less cement, and that can be through more effective mixed designs, but also supplementary cementitious material, which we're going to talk a little bit about here. But then another method is to offset or mitigate the carbon emitted. We have some techniques that we're seeing for that. And then also just to increase the strength and while reducing material use. So do more with less, which is part of where precast can really be an effective material for certain types of design, because it is so specific. It's plant produced and has the pre-stressing in it, so we can do more with less in terms of spans and things. So some of the things we're doing is trying to adopt less impactful versions of cement. So adoption of Portland limestone cement, or type 1L, and that can bring down the impact already. Using supplementary cementitious materials such as fly ash or slag in replacement of percentages of cement can also make a difference. And then trade-offs with SCMs can include impact the production process. So it's something you have to talk to your precaster about, how much of an SCM you can use, what kind of impact it's going to have on the cure time or on the aesthetics or on the performance of it. This is where things do move at sometimes what seems like a slow pace within the industry. It's because we have stuff that we know can effectively replace cement and have less of a carbon impact, but we need to also make sure that the performance, the strength, the curing time, and all the things that we need it to do are still there. So there's kind of that push pull between innovation and engineering to make sure that we're circling all the squares there. Um, so lots of great research going on and some different cement improvements that are already kind of being phased in. Portland limestone cement being a really good example because it's already becoming fairly commonly used. It's a blended cement with a higher limestone content. Works pretty much the same as Portland cement, at least in theory. It's a pretty much one-to-one replacement. Often needs only minimal adjustments in mix designs. This can reduce carbon impact by about 10%. And we're seeing lots of producers in different parts of the country beginning to use it. There's always, a little bit of kind of working around to make sure that the mix designs hit what you need it to do. Anything different is going to be a little, take a little time to adapt to. But it's a fairly low hanging fruit in terms of what we can do for some initial reduction. Something else that's in the works that's maybe a little further down the line for common use is what's called limestone calcinated clay cement, or LC3. This is based on a blend of limestone and calcinated clay, made using limestone and low-grade clays, which are available in abundant qualities. Cost effective, doesn't require a lot of capital intensive modifications to existing cement plants. This can reduce, or has the potential to reduce CO2 emissions by up to 40%. A little bit more complicated to figure out how to best use it in mixed designs, particularly with precast. So it's something that's around and kind of being examined, but not in as common of use at this point. Now, using supplementary cementitious materials is something the industry has been doing for a while. Fly ash is a very common example of that. It's a industrial coal waste, industrial coal byproduct essentially, that is used in replacement for percentages of cement. Another material that's used as an SCM is slag cement, a glassy granular material formed from iron blast furnace slag. Silica fume, and recycled glass. Like crushed glass pozzolan is used as a supplementary cementitious material in some projects that we've seen even around our region. Some other innovations in SCMs that are, kind of some cool stories of innovation and research that are going on. Basalt cement could be a more environmentally friendly cement than Portland limestone or Portland cement because it doesn't release carbon dioxide when ground into cement powder. Mine tailings. The Colorado School of Mines successfully developed a laboratory-based technique for utilization of mine tailings for production of lightweight aggregates for use in construction industry and has achieved the proof of principle milestone. Biomass is a biomass upcycled in lignin for decarbonizing energy-intensive materials is a research effort, by NREL and Department of Energy using lignin, an abundant waste material from pulp and paper products in replacement of cement. Microalgae. There's even some research being done, and I think some of it here in Boulder, for using this particular type of microalgae that actually grows limestone in the way that kind of coral grows. So it's like sort of an organic cement product, though, which is kind of an intriguing possibility. One of the really cool programs that's going on within our region too is we work with a professor at a university or at Idaho State University who is involved in a project called Sweetcrete, which is using some um, sugar waste products to use as a replacement of cement. So they're actually, in some pretty interesting grant funding right now and doing some work with DOTs. They want to use artificial intelligence to really optimize the concrete mix. And for the third part of the project's work with the Department of Transportation in Idaho, they're working with a sugar company for the materials. It's kind of an interesting potential circular economy approach to using a waste byproduct from another industry as replacement for cements in concrete. So there's some interesting things happening that we're hoping to see scaled and successful down the road. So lots of effort being put into finding ways that we can make effective concrete without using so much traditional Portland cement, which is the main driver of its carbon impact. Recycled aggregate, I mentioned briefly earlier that there is more research being done on actually crushing down concrete at the end of life and using a good portion of that as aggregate supplement in new concrete because there can be benefits for that as well. And I think I've heard of some mixes getting up to maybe 40% or something or with crushed aggregate. So it's kind of more of a cradle to cradle circular type of approach too. And then there are carbon capture technologies, which you may have heard of. I know some of this takes like industrial waste CO2 and captures it and injects it into concrete, and it's said to have some benefits for curing and durability and things. And it's a way to sort of entomb or capture concrete or the CO2 that goes into the atmosphere. And then ultra high performance concrete is kind of one of the earlier slides. I mentioned the idea of just trying to do more with less and use higher strength materials that use less going into it. And UHPC is an example of that. It has a minimum compressive strength of 17,000 pounds per square inch. It's like twice or more than that strong as traditional precast in that respect. UHPC building and bridge members will use materials more efficiently, be able to span farther, have lower consumption of construction materials. So this is something that some is being used in some types of applications, and it's just kind of a cool new potential technology for us too. So in summary, concrete is a durable, efficient material that inherently provides versatility, resiliency needed to meet the multi-hazard requirements and long-term demands of high-performance structures. Beyond excellent lifetime performance, the precast industry is innovating and working tirelessly to reduce its carbon impact in the short term as well. Lots of promising new technologies and techniques enable us to build for tomorrow. And with that, that's all I have. This is my contact information. If anyone wants to reach out to me afterwards, A, with questions, or B, with who are interested in GBCI certification or AIA or any of that kind of stuff, please feel free to reach out. And thank you.
Thank you, Jim. That was phenomenal. I know I learned quite a bit, and I'm excited to see what questions come in. So if you all have any questions, comments, please throw them in the chat or raise your hand. We're happy to um, open up the conversation now that we're in the Q&A portion of the topic. And with that, I do see at least one question in the chat so far. So I'll read them out to you, Jim. Feel free to view them
Yeah.
in the chat function and answer away.
All
So
right.
first, some thank yous. And so for folks looking to properly use the updated EPDs and early design LCAs, do you have a recommended assumption to convert quantities to weight for the EPD's declared unit?
Yes, I know that we have a declared unit. I want to say it's like a metric ton, and I don't remember off the top of my head. This I can follow up with you on that. See it. If I'll jot that down because I know it's somewhere in my notes. I don't remember off the top of my head. I do believe we have that. We are gonna. I will say that we are kind of in the process of putting together more out-facing information for specifiers and designers and engineers. Right now, as an industry, we are relatively new to these regionalized EPDs, and we're kind of just going through the process of teaching ourselves about them. So I know that we're going to be publishing additional materials that get into some of those specifics. I will say also that we have a sustainability on the PCI website, pci.org. We have like a sustainability landing page that I think has a lot of that documentation and probably answers to some of those types of questions.
Thank you. And for the next question, for early assessments, we tend to rely on BIM extracted quantities. For precast concrete, these are generally volumes. This person's looking for something more accurate than just using the density of normal weight concrete. Um, and they said if that's a good placeholder for early assessment, then that's fine. Just wanted to get your thoughts. So kind of following up on that initial question.
Yeah, those are both really good questions, and I will admit a little over my head in the engineering side of things. I'm happy to. I would encourage you to please email me because I can actually connect you with. I'm going to give a big shout out, by the way, to Thomas Ketron, who put together a bunch of the update slides at PCI. He's our sustainability director at PCI, and I suspect he has a lot more accurate answers than I'd be able to give you on that, and I'd be happy to connect you. So feel free to follow up because I know we have better information on that right now.
Awesome. Next question from Victoria. Thank you, Jim, for the presentation. I am most curious about the insulated precast concrete EPD. The industry average GWP is calculated using EPS insulation. For some projects, the design team has requested to substitute that insulation for other less carbon intensive ones. So first question being, how
Mm-hmm.
feasible is this for regional local precasters?
I think now, since we have these, and this will vary by precaster, because one thing that's different now, I will say, as an industry, we've gone into using this, kind of the WAP system, or these calculators that precasters are able to enter in this information and do more project specific EPDs based on what's going into that. So I think we have a heck of a lot more flexibility for the most part to do that now. Now, where it comes to some of these regionalized or industry wide EPDs, I mean, that's a little bit more locked in. But I would suspect most precasters you work with who have their own EPDs would be able to calculate what the difference would be with the different types of insulation used, because they have access to the system to do it.
Awesome. And following up on that, if you switch the insulation or thickness from the industry average, what is your best recommendation to what EPD proxy to use?
I would have to get you on that one too. I'm afraid I don't know the answer to that. Man, that's a good question though. Uh, and yes, please do follow up with me, because we have folks I can connect you with on that that would be able to help.
Yay. And then another one came in. Love the engagement. Thanks all.
Yeah.
Once again, thank you, Jim. This person's interested in the trade-offs with SCMs and SCMs that may undergo carbonation prior to use.
Mm-hmm. Yeah, this is really where it does get fascinating, because there's all these different SCMs that can do all kinds of cool things, but there are it can change how it can change aesthetics, it can change performance. The thing that really is an issue in the precast industry specifically is that we have to think about cure time, because some of these SCMs do significantly slow down the amount of time it takes to cure. And just the way our model works, because the way our precasters are set up, it is a modular offsite construction method. It's kind of based on like being able to turn the beds in 8 hours. Like it has to get done in that time. So this is where in the past, when we weren't thinking about any of this kind of stuff, it was just, oh, dump as much cement as possible into there to make it move faster. But now we have a lot more sophisticated ways of moving that needle. But it can be sometimes a limiting factor in how much SCM we can use and how we can use it. So there are different types of performance factors that we have to think about. Some are more proven out than others. To me, where the real fascinating work is right now is finding out which of these lab experiment kind of things can really like take hold on a large scale level and help us make a difference.
Yay. Thank you. Awesome. Another one. So, what is the current status of the industry in terms of energy sourcing for cement production? Does it just match the averages, the grid averages for coal, gas, renewables? Is that part of the carbon reduction focus for the concrete industry? Basically, what are the goals?
Yeah, that's a good question too. And I think that and I wouldn't, this is one of those areas where like the cement industry is, we work with them. They're a little bit different animal in how they manufacture their part of it. I know that it's on their radar. It's part of the like PCA's roadmap to 2050 roadmap to carbon neutrality. I know that it is part of what's reflected in our regional EPDs in terms of different energy generation capabilities in different parts of the country. So I would say that for us on an industry level, we're a little bit our producers are at this point, I think, controlling what they can control in their scope, but and that's, I know it's on their radar because it is a significant, it's at least a significant enough piece of, if you look at some of those charts, the energy is a significant enough piece of it to want to make a difference there. I think what's really helpful about this being able to get more granular in the data that we have and understanding where the different GWP impacts are and seeing how much, okay, energy has this much, transportation has that much. It shows us where we can start to make a difference. So my suspicion is that now that we understand it a little bit better, it will become more of a focus point for a lot of producers who are looking to find anywhere they can to bring down the percentage, because that's where it's going to come in. There'll be certain areas where, okay, maybe if we can get to more renewables, that makes enough of a difference that it allows us some flexibility in a different area of production.
Awesome. Well, that brings us to the top of the hour. Thank you again, Jim, for taking time out of your busy schedule to educate us. I found it highly engaging, and I'm hopeful that our audience did as well.
Thank you. Appreciate you guys having me. I appreciate it, Bailey. Thank you.
Wonderful. And yes, for everyone on the call, I will follow up, CLF will, with a recording of today's webinar. It'll be posted to our YouTube and I'll send it out in an email so everyone can review it as needed. And other than that, thank you all for joining us. I hope everyone has a great rest of the day.
Bailey, I wanted to quick give a big shout out to thank you, Jim, for the presentation. That was awesome. But also I wanted to recognize a few of the CLF Rocky Mountain members, which are not on the call today, but Jay Ahar from CU Boulder and Alexis Feitel and Michael Lyons because of their great work on the SEE pre-standard that was released and Bailey mentioned here. So we have a lot of great collaboration besides also Matt Young Claus that is here on the call that also collaborated with RMI and Victor Olgate as well. So thank you all for your awesome work and keep it up.
Thanks for that shout out, Victoria. Sweet.
All
Until
right.
next time, everyone, have a good one.
Cheers. Have a good afternoon, everybody. Thanks.